Hello and welcome back to my channel. Today we are looking at a very iconic sound card, the Sound Blaster 16. Now this card comes from the scrapyard and unfortunately it doesn't work. We will get to what is the problem in a moment, but first let's talk a little bit about this sound card. This sound card was released in 1992 and I have revision 6 from the 46th week of 1993. So this is not an early version, I think. And there are later models of Sound Blaster 16, including all the Vibra variants. And I think there's a CT4400 something as well. This sound card was hugely popular. And it also contributed to Creative's revenue growth from around 40 million US dollars per year to around 1 billion after the Sound Blaster 16 was released. This gives you an idea how popular this card was. In fact, it was so popular that most of the emulation programs today are having some sort of a Sound Blaster 16 compatible version you can pick from to emulate a sound card for your games. Now, this card also comes with a real Yamaha OPL3 chip, and we have an IDE port here. I don't think you could hook up any CD drive to this IDE port. I think it is limited to Panasonic drives, but I'm not sure. Maybe in the future we will try to figure this out. I have to admit I'm not an expert when it comes to sound cards. I'm just very frustrated that it doesn't work because this card looks and feels very premium. I rarely had a sound card in my hands that felt so robust and of high quality. Now, what's wrong with it? Unfortunately, the output is very noisy. And I'm not saying like a little bit noisy what you would expect from these cards. No, there is static. You can literally hear about 70% static when there is a sound being played. It is worse for 8 and 16-bit audio. I think the OPL3 chip, the FM synthesis is a little bit better, but it still has an issue. Now, of course, I did some research because I have absolutely no idea what I can do to figure out what is at fault here. And many people seem to have issues with these chips here. There are 4 of them on the board, and they are Opamps, operational amplifiers. Now, I poked around and tried to figure out where the noise that arrives here at the speaker out jack is generated on the board. And my guess right now is this chip. We will look at the oscilloscope output in a moment, and hopefully I can show you how I came to suspect this chip. But I think first what we want to do is to listen to this card, how it sounds right now, and how it will sound once we start changing parts on that card. Unfortunately, I don't have replacement op amps, so if I do replace this chip, I probably have to replace it with another chip that is on this card. And if I go to replace this, I will replace it with this one, because as far as I understand, these op amps, they take different responsibilities. Maybe one of them is responsible for the synthesized sounds that come from the Yamaha chip. Another one is responsible for the digitized sound. And a third one here is responsible for whatever is generated on the wavetable. And then it goes through a bunch of filtering capacitors until it reaches the output. I'm not sure if this is correct. Please correct me in the comments if I'm wrong. But this is what I can think of right now. So let's plug this card in the system and listen to how it sounds. Okay, so the card is plugged into the system. I connected my speakers or the recording device to the speaker out. I also disabled the amplifier on the card, so I'm just using the line out feature of this card. The volume wheel will have no effect on the output signal. That usually generates a cleaner output. And now let's hear what sounds this card produces when we play some samples. Okay, and this is already the output of the sound card. You definitely hear some static noise in the background. So let's see when the card initializes how we hear some fluctuations in the output. And we're silent. There's still something going on, but it is a lot better than before. Okay, so here we are. Now we can pick from our 8-bit, 16-bit, and synthesized music. So let's try 8-bit. We'll try both channels.
8-bit testing.
And we have a very elevated noise level now.
8-bit testing.
So something is definitely not right. Let's try 16-bit. It will not be much different.
16-bit testing. 16-bit testing.
So yeah, this is very noisy and something is going on with this card. Now let's try the synthesized music. This noise comes after I play synthesized music, this. Let's try that one more time. This. No idea what this is, and again we are in elevated noise levels. So yeah, there's definitely static on this card that is generated somewhere. Now the goal is, and I have never debugged a sound card before, but what I want to look for is where is this noise generated? Somewhere I should see with an oscilloscope where these waveforms are generated and then they come to our output. So let's have a look at the card and probe around with an oscilloscope. Okay, I have a complete new setup here. It's just put together very quickly, sorry for that, but I'm trying my best to show you what I have found so far. I'm using wireless microphones right now, so let's see how this one will work out when I'm working away from my desk. Okay, so let's try to play the synthesized music one more time. You already can hear the static noise in the background. So maybe it's related to capacitors, I have no idea, but let's just see how this noise looks like when we go and measure our output jack here. I think here is a signal that I can use. Let's readjust. So here you can see the noise level from our jack, and the other side is the same. And then you obviously can poke around and find, for instance, a left and right channel here. These are two inductors. If you go here, you have the same signals. They basically go to the left and right channel on our output jack. And then you go through all kinds of other electronics here. But the one I found was this connection here. Now this one looks like it has our static noise. Now if I play the sound one more time, so you can see this is the output of the sound on the oscilloscope. And then it's silent again. And here was our small blob at the end of the sample. So where does this point connect to? That point connects to this op-amp, this chip here. And that is why I want to try to replace this op-amp with the one that is here in the bottom right corner, because I don't use this, I believe. It's next to the wavetable header, and I believe all these op-amps have different tasks. So if I look at any of the other op-amps right now, they're all silent. This is plus 48 millivolts. This one here stays at minus 700 millivolts and is just going up and down and up and down. Here's another one. Nothing. And this one. Also nothing. So what I will do now is, first of all, I don't want to poke around on a running system anymore, and I want to see what happens if I replace this op-amp with the one that I think is not really used for the things that I want to test right now. But before we continue, a big thanks to PCBWay for sponsoring this channel. If you're into electronics, whether it's creating custom PCBs for retro hardware projects or tinkering with new designs, PCBWay has you covered. PCBWay offers high-quality PCB manufacturing, prototyping, assembly, and even 3D printing at affordable prices. But that is not all. PCBWay offers other services like CNC machining, sheet metal fabrication, and injection molding. And if you're in need of some inspiration, you can always head over to PCBWay's shared project space and look for ideas. Check them out using the link to PCBWay.com in the video description. Okay, then let's have a look at our Opamp chip. It was this one here. So this is the chip. This one here is the chip where I measured these weird frequencies, even though I didn't play any sounds. This is the pin, this is an output pin, and I think it should be fed by these two, but I couldn't notice any input that had that weird frequency going in, that it should come out from this pin again. So chances are that this entire chip here might have an issue. And now I can see that our chip here is right next to some capacitors. Yeah, I should be able to get in there with some low melt solder. And then we can try to get rid of this chip, clean up the pads, and then we will steal this chip, this one here, that is right next to the wavetable. Maybe I'll not even put this chip back. Let's see if the sound card will also work without it. So then let's add some low melt solder and lift this chip. And now we'll add the low melt solder. Okay. Same here. Okay. I think we need more thermal mass here, so I'll just add more low melt solder. It will just remain liquid for longer then. This was too less. So now I think we should be fine. Let's try. Here we are. So, chip is out. There is a indicator here that the chip has to go in like this. Oh. Of course, we need some flux, so we'll do opposing corners first. Makes it easier to adjust in case we have to. Okay. And now we can easily do a little bit of drag soldering. Okay. So here's our chip on the board now. Let's try the card if we get a different output. And this spot remains empty. Let's see, 8-bit digitized sound.
8-bit testing.
Oh no, it's still there. So that was not the issue.
16-bit testing.
Ah, that's sad. Okay, so this wasn't the issue. The same problem there. I think I should still continue to look around that area, and I have to put this other chip back on the card. Okay, clearly swapping these op amps didn't change anything, so I went ahead and removed the amplifier that is here. I also had to remove 3 capacitors on this side and 2 capacitors here, otherwise I wouldn't be able to get this amplifier out of this board. There are very large ground planes connected to this chip, and I was inclined to add a socket here But I spoke to Tony, and he recently fixed a sound card. And some of his viewers said that do not put a socket here because these ground planes that are connected to this chip are on purpose. It serves as a heatsink. So if you have a card like this and you have an amplifier chip, do not put a socket there. Okay, but why did I remove this chip? Well, the thing is, here are jumpers where you can enable and disable this amplifier circuit. And right now in this position, to the top, so these jumpers are shifted to the top, the amplifier is disabled. However, the chip is still connected to the circuitry. So I thought maybe this has an effect and maybe the chip is faulty and causes all these distortions that we heard from all the samples we played. I will try this card as it is right now. We will see if this works. But if it doesn't give any output, then, well, maybe I removed one of the capacitors here that could have been a high-pass filter or something else. So I do not want to spend too much time on it because there is another hint I got while talking to Tony. And now you will hear some reference to software design. Tony was my rubber duck. I tried to explain to him what the issue is on the sound card. And he also looked over a little bit of the footage that I sent him. And he told me, hey, look, your audio signal is in the negative voltage. That shouldn't be the case. But we will get to this after I quickly test this card in this state right now. So let's see what happens.
8-bit testing. 16-bit testing.
So unfortunately, removing the TIA 2025 amplifier chip did not change anything. The card still sounds the same and we still have the distortions, we still have this blob at the end of the FM synthesizer. So there is nothing that really improved by removing this amplifier chip. Okay, then let's quickly check what is going on with our voltage regulators. There are two voltage regulators here. This one here is a 9-volt regulator, and this one here is a 5-volt regulator. Both of them are being fed by the 12-volt line. The center pin is ground, so if I go ahead and measure here, we get 12-volt input, and we get 9 volts out, almost 9 volts. Now this regulator is flipped, so on this side we will get 12-volt input, and here we get 2.5. That is not correct. So we have to focus on this regulator and maybe the circuit that's around it. I checked the entire board with a thermal camera and I was not able to figure out a component that is faulty. Nothing heated up in a way that would maybe suggest that there is a short or something that's a problem. So what I will do now is I will take the card and I will remove this voltage regulator and then we will see how it behaves when I put it into a test circuit. There we go. Okay. Now we'll clean this up and then we'll have a look at this regulator. Okay, I hope this makes now a little bit sense. You can ignore everything that is to the right here. We only focus on our regulator here, and I have a multimeter hooked up here, and this wire here is for the power supply. This is coming from this voltage adapter here. This is something that I use for an exhaust for the fumes of my soldering. But anyway, it will serve for this purpose of this demonstration. So let's switch on the multimeter and measure the voltage that is the input right now to the regulator. So let's just see. Okay, it's very difficult to see here. It's 4.7 volts. Okay, we get 4.8. And let's see the output. Of course, it's a 5-volt regulator. It will not have 5 volts. There's a drop as well. It generates 3.6 volts. That's already higher than what we have seen on the sound card. That is not good because I couldn't see anything with the thermal camera. I wonder if there was something else problematic on the sound card. But anyway, let's continue now and increase the voltage. So we have 5 point, well, you can see it here. You have to trust me now that this is the same value here. So we have maybe, let's say 7.5 volts, let's say. Let's see what happens to the output. And the output is exactly 5 volts. So now it looks like the regulator is working well. 100 ohms. This is a good value resistor. We'll try this one. 5 volts output with an input voltage of 7.5. So let's see if we put a load between ground and the output. So there's not even a drop in voltage. And I feel the resistor is getting slightly warm. Yes, it does get warm. Not too much, but it gets warm. So the regulator definitely delivers the voltage that is shown here. Well, and now comes another philosophy that you learn when you're in software development. If you are going to try to reproduce something, make sure that your test environment is exactly the same as it is on production. You have seen that I only have 7.5 volts here right now. So 7.5 volts input, but on our card, we have 12 volts input. So let's continue and measure the output voltage and increase the volts on our input. Now we're at 8. Now we're at 8.5, 9.5. Now we're at 10 volts input. Oh. At 10.5, the voltage fell off a cliff. So at 10 volts, we get an output of 5. And you see now I moved a little bit and the voltage dropped by these, 20 millivolts or something. I'm moving just a little bit. And you can see that the voltage is dropping. I'm really moving only very slowly. 100 millivolts, and there you go. Now you're dropping off a cliff. 4.2. It's just the pressure on the dial causes this regulator to lose that much voltage. I'm not turning it at all. Somehow it powered off, and now you can see 2.5, 2.6 volts. This is what we had on the card as well. So this is really me just pressing on the dial. I guess this is a failsafe, and I'm happy that it did this, because otherwise if it would just short, or, well, the worst case would have been if it just lets the 12 volts that are the input through to all the chips that are connected to it, because I think half of the chips on the Sound Blaster 16 are powered by this regulator. So yeah, now all I can do is wait for a replacement. And by the way, just in case you're wondering, this thing is completely cold. There is nothing going on this regulator, so there is no short or whatsoever. This seems to be an internal protection that is triggering. Let's hope that this is our problem. I managed to get replacements. So I already took one out. This is a 5 volt linear voltage regulator. Now here's our broken one. Let's double check what the behavior of this broken part is. So here you can see the voltage 4.7, 5, 6, 7. We are getting an output of 5 volts. 8, 9, 10. And now it slowly starts dropping, and then it completely, around 10.5, it shuts off. There you go. So now the voltage regulator no longer functions as a voltage regulator. So here's our broken one. Now comes in the new one. There we go. And let's try the same thing. So 4.7, yes, we have a voltage drop here. Of course, it can't regulate to 5 volts if you're too close to 5 volts. There's always a little bit of a voltage loss. But now at 6, 7, so we're around 4.8. 9 volts, 4.8, 10, and we are past the critical area where the old part was failing. And we should have 12.2, 12.1, 12.2, and the voltage regulator is still outputting 5 volts. So, yeah, I think here I just have now a little bit capacitance or ground or whatsoever when I touch this one, and then suddenly it's 5 volts. So I guess when this part is back on the board, it will work properly and we will have, hopefully, a working Sound Blaster 16. I think that's pretty good. Yeah, I think that will work. So, oh no, these legs are a little bit thicker. Well, not too much. Okay, that's actually perfect. It fits perfect. Okay, so old and new. I will also add some thermal paste under this regulator. Maybe this regulator does get hot, I'm not sure. But I tested this on a Voodoo 3 and it was a PCI card. It has this voltage regulator on the card. And with a little bit of help from thermal paste, you could actually drop the temperature of a passively cooled regulator by 20 degrees lower. So instead of 95, I think it was 75. So let's add a blob of thermal paste here. And that's it. We don't need more. That probably will get squeezed out on the sides. Okay, next is the screw. There's a small screw that holds this entire thing in place. Never was that simple in any of my repairs. There was just a voltage regulator. Okay, so I see now that this voltage regulator is having a thinner tab compared to this one, so the screw is a lot further out, so maybe we can do something about this. But I think a better solution is just to use a shorter screw. So this one should work well enough. So this one should be long enough to come out on the other side, and yes, that looks not too bad. One final twist with a screwdriver. And now all that's left is to solder this regulator to the board. I never had a repair like this. Never. This is the first one that a regulator fails. And it does make sense, or it would make sense, because I tried to run a Sound Blaster 2.0 one time without the negative 5 volt rail, because modern ATX power supplies no longer supply the minus 5 volts on the power connector. So you need an adapter that generates that for you, otherwise that sound card doesn't work. And if you operate the Sound Blaster 2.0 without, you will get a very similar distorted, maybe silent output with a lot of static. And I think that's it. Now I'll just have to cut off the legs a little bit, clean it up, then I will inspect the solder joints and we can test this card. Hopefully it works. Okay, the card is in the system. Let's see what is going to happen. Okay, it finds the card. That's good. DSP version 4.12 is something that we will have a look at in a future video. Version 4.12 is suffering from the hanging note bug, and there is a way to fix it, but this is something for later. Let's test our sound card now. What will we hear?
8-bit testing.
No, it works.
16-bit testing.
I hear absolutely no noise. It isn't even a reference voltage, it is just the voltage that powers all those chips on the card. So here it is. Why am I making these videos? Why do I show faults before I fix them? If you have a card like this with a similar symptom, check the voltage regulators. That's it, as simple as that. Maybe it's not as bad, but maybe you have a very noisy Sound Blaster 16. Check the 5-volt regulator. Maybe instead of 5 volts, you're getting 4.5, 4.7. I don't know from which level it sounds noisy or whatsoever. And yeah, this is all I have for you in this video. Now let me know in the comments what you think about this project. If you like the content, give this video a like, and if you want to support my work, you can head over to Patreon. There are a few tiers you can pick from, or you can sign up for free. I will post from time to time also free content. And yeah, I will go ahead and enjoy a little bit of Sound Blaster 16 sounds. Thank you so much for your time, thanks for watching, take care, and bye bye.